Welcome to G Fun Facts Online. When we look up at the night sky, we are observing a universe that, by all rights, should not exist. The stars, the galaxies, the planets, and the biological machinery of our own bodies are anomalies in the grand mathematical equations of the cosmos. According to the foundational principles of physics, the Big Bang should have produced equal amounts of matter and antimatter. Because these two cosmic counterparts annihilate each other upon contact, leaving behind only a flash of pure energy, the universe should currently be a vast, dark, and empty void filled with nothing but aimless, cooling radiation. Yet, here we are. You are sitting at a screen made of matter, receiving information on a planet made of matter in a universe dominated by matter. Where did the antimatter go? What tipped the cosmic scales so profoundly in our favor? This conundrum, known as the Baryon Asymmetry of the universe, is arguably the greatest existential mystery in modern science. For decades, physicists have scoured the cosmos and smashed particles in giant colliders, hoping to find the precise mechanism that allowed matter to survive the fiery crucible of the early universe. Today, the most compelling answer to this ultimate question points to the smallest, most elusive, and most mysterious particle ever discovered, the neutrino. The quest to decode the matter-antimatter imbalance has led scientists deep underground, into the realm of ghost particles, oscillating identities, and a phenomenon known as neutrino CP violation. If current and upcoming mega-experiments can definitively prove that neutrinos behave differently than their antimatter counterparts, we will finally possess the Rosetta Stone of our cosmic origins. To understand why neutrinos are the prime suspects in this cosmic whodunit, we must first understand the strict rules that govern the creation and destruction of matter. In 1928, British physicist Paul Dirac wrote down an equation combining quantum mechanics and special relativity to describe the behavior of the electron. The mathematics worked flawlessly, but it harbored a startling quirk. It had two solutions. One described the electron we know, with its negative charge. The other described a particle identical in mass and spin, but with a positive charge. Dirac had unwittingly predicted the existence of antimatter. Just 4 years later, the positron was discovered in cosmic rays, proving Dirac right. We now know that every fundamental particle in the Standard Model has an antimatter counterpart. When energy condenses into matter, as it did in the unimaginably hot, dense fractions of a second following the Big Bang, it must do so symmetrically. For every quark forged, an antiquark must be born. For every electron, a positron. However, we observe a universe where matter outnumbers antimatter by a staggering margin. The survival of our material universe requires a fundamental asymmetry, a flaw in the mirror of reality. In 1967, the brilliant Russian physicist and dissident Andrei Sakharov formulated 3 absolute requirements, now known as the Sakharov conditions, that the universe must have met to generate a matter-dominated cosmos from an initially symmetric state. First, there must be baryon number violation, meaning a physical process that produces more baryons, which are matter particles like protons and neutrons, than antibaryons. Second, there must be C and CP violation. The laws of physics must distinguish between matter and antimatter, known as charge conjugation or C violation, and must not be perfectly symmetrical when viewing a particle and its mirror image antiparticle, known as charge parity or CP violation. Third, these processes must occur out of thermal equilibrium. The processes creating this asymmetry must occur rapidly in a cooling, expanding universe, preventing the newly formed matter from immediately annihilating with antimatter and returning to equilibrium. Physicists initially hoped that the quarks, the building blocks of protons and neutrons, would provide the necessary CP violation. In the 1960s and 70s, experiments did indeed show that quarks and antiquarks decay at slightly different rates, a discovery that earned Makoto Kobayashi and Toshihide Masukawa the Nobel Prize. However, when scientists calculated the magnitude of this quark CP violation, the results were disheartening. The asymmetry was millions of times too small. It could account for a tiny fraction of a galaxy, but never the entire observable universe. The Standard Model of particle physics had failed to explain our existence. The true architect of the matter-antimatter imbalance had to be hiding elsewhere, operating in a sector of physics we barely understood. If quarks could not explain the universe, physicists had to look to the other major family of matter particles, the leptons. The most famous lepton is the electron, but its sibling, the neutrino, is vastly more abundant and infinitely more secretive. Neutrinos are everywhere. They are born in the nuclear furnaces of stars, in the violent explosions of supernovae, in the radioactive decay of elements within the Earth, and in the upper atmosphere when cosmic rays strike air molecules. Every second, approximately 100 trillion neutrinos emitted by the Sun pass through your body. You do not feel them because they interact with normal matter via the weak nuclear force and gravity alone. A neutrino could travel through a block of solid lead a light-year thick and have only a 50% chance of hitting a single atom. This ghost-like etherealness makes them incredibly difficult to study. For decades after their theoretical proposal by Wolfgang Pauli in 1930, neutrinos were believed to be completely massless, traveling exactly at the speed of light. The Standard Model was built on the assumption that neutrinos had no mass whatsoever. Furthermore, neutrinos come in 3 distinct flavors, corresponding to the heavier leptons they associate with: the electron neutrino, the muon neutrino, and the tau neutrino. At the turn of the 21st century, a revolution in particle physics upended everything we knew about these ghosts. Monumental underground detectors, such as the Hyper-Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada, made a shocking discovery. Neutrinos change flavor as they travel. An electron neutrino born in the core of the Sun can arrive at Earth as a muon or tau neutrino. In the bizarre rules of quantum mechanics, this neutrino oscillation is only possible if neutrinos experience time. And according to Einstein's theory of relativity, a particle can only experience time if it travels slower than the speed of light, which in turn means the particle must have mass. The discovery that neutrinos have mass, albeit vanishingly small, at least 1,000,000 times lighter than an electron, broke the original Standard Model and won the Nobel Prize in Physics in 2015. This revelation was the crucial first step towards solving the antimatter mystery. If neutrinos could oscillate, they possessed complex quantum states governed by a mathematical matrix called the PMNS matrix. Embedded within the mathematics of this matrix was a placeholder for a specific variable, the carbon monophosphide violating phase. If this variable was non-zero, it would mean that neutrinos and antineutrinos oscillate at entirely different rates. The theoretical framework that connects neutrino CP violation to the survival of matter in the universe is a profoundly elegant concept called leptogenesis. To understand leptogenesis, we must journey back to the first trillionth of a second after the Big Bang. The universe was an unimaginably hot, dense soup of fundamental particles. According to a widely accepted extension of the Standard Model known as the seesaw mechanism, the lightweight neutrinos we observe today have extremely heavy, unstable counterparts. These heavy, right-handed neutrinos existed only in the ultra-extreme energy environment of the early universe. Because they were so massive, these heavy neutrinos decayed almost instantaneously. But if the laws of physics violate CP symmetry in the neutrino sector, these heavy neutrinos would not decay symmetrically. For example, they might decay into a normal lepton, like an electron, slightly more often than they decay into an antilepton, like a positron. This asymmetric decay satisfies all of Sakharov's conditions. It occurs out of thermal equilibrium as the universe rapidly expands and cools. It violates lepton number, and it violates CP symmetry. The result is a universe left with a slight surplus of leptons over antileptons. But a lepton asymmetry is not a baryon or matter asymmetry. We need protons and neutrons to build stars and planets, not just electrons. This is where the universe employs a spectacular quantum loophole known as the Sphaleron process. At the extreme temperatures of the early universe, sphalerons act like a cosmic balancing mechanism. They are non-perturbative interactions that smoothly convert leptons into baryons, and vice versa. When the sphalerons encountered the excess of leptons generated by the heavy neutrino decays, they washed this imbalance into the baryon sector. They converted a portion of the extra leptons into extra quarks, establishing the baryon asymmetry that eventually formed the matter-dominated universe we inhabit today. Leptogenesis is a mathematically beautiful theory. It seamlessly ties the microscopic mystery of why neutrinos are so staggeringly light, through the seesaw mechanism, to the macroscopic mystery of why the universe exists at all. However, physics is an empirical science. A beautiful theory is nothing without experimental proof. To prove that leptogenesis is the mechanism responsible for our existence, we must prove that CP violation exists in the neutrino sector. Measuring CP violation in neutrinos requires comparing the oscillation of neutrinos with the oscillation of antineutrinos. If the probability of a muon neutrino turning into an electron neutrino is perfectly equal to the probability of an anti-muon neutrino turning into an anti-electron neutrino, then CP symmetry is conserved and leptogenesis loses its strongest foundation. If the rates differ, CP symmetry is violated. Because neutrinos interact so rarely, measuring this difference requires generating the most intense beams of artificial neutrinos ever created and firing them through hundreds of kilometers of solid rock into giant underground detectors. Leading the charge in this global scientific endeavor is the T2K experiment, which stands for Tokai to Kamioka in Japan. T2K fires a beam of muon neutrinos, or antineutrinos, from the J-Park Accelerator Complex on the east coast of Japan, 295 kilometers across the country, to the Super-Kamiokande detector buried deep beneath Mount Ikanoyama. In 2020, the T2K collaboration published a landmark paper in the journal Nature, sending shockwaves through the physics community. By analyzing years of data, they found that muon neutrinos were transforming into electron neutrinos at a significantly higher rate than anti-muon neutrinos were transforming into anti-electron neutrinos. The results excluded CP conservation at a 90% confidence level and certain values at the 99.7% or 3 sigma level. The data strongly preferred a maximal negative CP violation, a finding that perfectly aligns with the requirements of leptogenesis. However, in particle physics, a 90% or even 99% confidence level is not enough to claim a definitive discovery. The gold standard is 5 sigma, representing a 99.99994% certainty. To bridge this gap, the T2K experiment has recently undergone a massive upgrade, entering a new phase of enhanced sensitivity. Between 2024 and 2026, the collaboration dramatically increased the power of their neutrino beam. By upgrading the electromagnetic horn system and pushing the current from 250 kiloamps to 320 kiloamps, they achieved a continuous beam power of 760 kilowatts, significantly boosting the number of neutrinos fired toward the detector. Furthermore, they installed a state-of-the-art near-detector complex equipped with a super fine-grained detector and high-angle time projection chambers. This near-detector measures the raw neutrino beam before it oscillates, drastically reducing the systematic uncertainties caused by complex neutrino-nucleus interactions. With these upgrades, T2K continues to gather the crucial data needed to tighten the noose around neutrino CP violation. While T2K pushes the limits of current technology, the definitive proof of neutrino CP violation, that coveted 5 sigma discovery, will likely fall to the next generation of mega experiments currently under construction. These are the Deep Underground Neutrino Experiment, or DUNE, in the United States, and Hyper-Kamiokande in Japan. DUNE is the flagship project of Fermilab and the U.S. Department of Energy, and it represents an unprecedented leap in particle detector technology. Expected to begin major cryostat construction in 2026, DUNE will utilize a staggering 1,300-kilometer baseline. A high-intensity wideband neutrino beam will be generated by the upgraded PIP-2 accelerator at Fermilab in Illinois, delivering 1.2 megawatts of power, which is upgradable to 2.4 megawatts. The beam will travel straight through the Earth's mantle to the Sanford Underground Research Facility in Lead, South Dakota. Awaiting the neutrinos 1.5 kilometers below the surface of South Dakota will be 4 colossal detector modules. Unlike water-based detectors, DUNE will utilize liquid argon time projection chamber technology, holding a total of 17 kilotons of liquid argon in its fiducial volume. When a neutrino interacts with an argon nucleus, it produces a shower of charged particles that ionize the liquid. High-voltage electric fields drift these electrons to highly sophisticated sensor planes, allowing computers to reconstruct the neutrino interaction in stunning, high-resolution 3D detail. This technology allows DUNE to distinguish between electron neutrinos and background noise with unprecedented precision. In the most favorable scenarios, if the carbon monophosphide violating phase is indeed maximal as T2K hints, DUNE could surpass the 5 sigma discovery threshold in just a few short years of operation. Meanwhile, in Japan, Hyper-Kamiokande is being excavated. Operating on the same principles as Super K, but scaled up to gargantuan proportions, Hyper K will boast a fiducial volume 8 times larger than its predecessor. Working in tandem with the upgraded J-Park beam, Hyper K will collect neutrino events at a staggering rate, systematically crushing the statistical uncertainties that currently limit our understanding of the carbon monophosphide violating phase. As massive accelerators and underground tanks hunt for the carbon monophosphide violating phase, another class of experiments is searching for a different, equally vital piece of the leptogenesis puzzle. For the seesaw mechanism and leptogenesis to work, neutrinos must possess a property unlike any other matter particle. They must be Majorana particles. Proposed by the enigmatic Italian physicist Ettore Majorana in 1937, a Majorana particle is a particle that is its own antiparticle. Because neutrinos have no electric charge, there is no fundamental conservation law preventing a neutrino and an antineutrino from being the exact same entity, differing only in their quantum helicity, which is how their spin aligns with their momentum. If neutrinos are Majorana particles, it would prove that lepton number is not a strictly conserved quantity in the universe, a vital prerequisite for leptogenesis. To test this, physicists are searching for a theoretical, ultra-rare radioactive decay known as neutrinoless double beta decay. In standard double beta decay, 2 neutrons in a nucleus simultaneously decay into 2 protons, emitting 2 electrons and 2 antineutrinos. If neutrinos are their own antiparticles, however, the 2 antineutrinos emitted in the nucleus could theoretically annihilate each other before escaping. The result would be the emission of 2 electrons and 0 neutrinos. Experiments like LEGEND, which stands for Large Enriched Germanium Experiment for Neutrinoless Double Beta Decay, are operating in deep underground laboratories, shielding ultra-pure germanium crystals from cosmic rays and background radiation, waiting years in the dark for a single nucleus to undergo this prohibited decay. A confirmed observation of neutrinoless double beta decay would prove that neutrinos are Majorana particles, confirming the bedrock assumption of leptogenesis and securing the neutrino's role as the architect of matter. The investigation into neutrino asymmetry is not merely an esoteric pursuit of subatomic bookkeeping. It is a profound quest to understand the architecture of reality. The universe we inhabit is a delicate, razor-thin exception to the rule of absolute annihilation. Every star that ignites the dark, every planet that harbors oceans, every strand of DNA that replicates, and every human mind that looks up at the sky is the direct result of a microscopic imbalance that occurred when the universe was less than a trillionth of a second old. As we approach the latter half of the 2020s, the scientific community stands on the precipice of a paradigm-shifting revelation. With T2K's upgraded 760 kilowatt beam pushing current limits, the impending construction of DUNE's massive liquid argon chambers in South Dakota, and the excavation of Hyper-Kamiokande, the net is closing around the ghost particle. If these international collaborations successfully map the carbon monophosphide violating phase of the neutrino, and if experiments like LEGEND prove the Majorana nature of the particle, we will finally have a complete, mathematically rigorous narrative of our genesis. We will have proven that the lightest, most weakly interacting particle in the known universe, a particle that passes through us by the trillions without a trace, acted as the cosmic fulcrum that allowed existence to triumph over nothingness. The story of the neutrino reminds us that the cosmos is governed by a breathtaking interconnectivity. To understand the grandest structures in the universe, the vast superclusters of galaxies, and the very presence of matter itself, we must look to the infinitely small, decoding the quiet, asymmetric whispers of the ghost particles that survived the Big Bang. Thank you for tuning in to G Fun Facts Online. Keep looking up and stay curious.